Welcome everyone to Mount Cuba's virtual public night number, I've lost count. Thank you to anyone new who is joining us this evening. We are going to have an exciting program this evening. As we normally do, I will have you guys mute yourself when the program starts. If you have questions, you can send them directly to me, Kim Green, in the chat, and I will dish them out to John as we go. He may have times where he may take a break to let you ask questions, and then we can do it that time, and then you can also hold your questions to the end. And with that, I am going to go ahead and turn tonight's program over to John.
Okay, thank you. I hope you can all hear me. So my name is John Gizis. I'm a professor at the University of Delaware. And tonight's topic is a very special star named TRAPPIST-1. As we'll see, it's special because it has 7 Earth-sized planets orbiting it. And so in many ways, it's the most interesting planetary system we know about other than the sun. Of course, those are fighting words among astronomers, but it's a pretty good system. So many of you may know all of this already, but when you look up at the sky at night, many of the stars that you see with your own eye are actually relatively far away. The nearest stars can often be too faint for the human eye to see. So even though they're closer than the stars we see at night, they end up being dimmer. One classic example of this is the nearest star to our solar system, a star that has the name Proxima Centauri. It is, by astronomical standards, very close. It's just 4 light years away, meaning, on the other hand, that it is so far away that it takes 4 years for light or a radio signal to reach us from there. By comparison, of course, the sun is only 8 minutes away, and the moon is 1 second away. So 4 years is very far indeed, but by astronomy standards, it's nearby. So this is, of course, a very interesting star system. You can pick it out because it moves along. So here's pictures from an astronomer who took them over 10 years with the same telescope. And so you can see that most stars are staying in the same place in the sky. And then this one that doesn't look particularly interesting or bright is moving along very rapidly. And that's oftentimes the sign that a star is nearby. But because these types of stars are so faint, discoveries of them have gone on until recent years. Proxima Centauri, just to give you some background, like most stars that are less massive than the sun, has at least 1 planet around it. We call this a super Earth, not because it's better than Earth, but because it's larger than Earth, or rather it's more massive than Earth. So that discovery was based on the motion of the star, and we can't actually see or measure the planet itself. So a picture like this one, or a picture like this one, which were all put out in the big press releases and stories about the discovery of this planet, actually have very little basis in reality. We know next to nothing about the planet, except for a guess at how massive it might be. So that's the context setting us for another star, which until about 5 years ago had the very boring name of 2-mass J2306, blah, 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 right? And it happened to be that I was leading the team that discovered it. So even I say blah, blah, blah. It's not a very good name, as we'll see. And today it's more better known as TRAPPIST-1. So I can tell you about the discovery of the star. Just like our pictures that we saw earlier for Proxima Centauri, if you take pictures taken many years apart, you can actually see the star moving. Except there was a bit of bad luck. So it's very hard to pick out, for example, in this 1953 picture that's on the left-hand side of my screen. Maybe it's the right-hand side of yours, right? Anyway, it's labeled 1953. In the middle, I've put together a 1982 and a 1991 image where I hope you can see now that there's a star moving there. The stars in this image appear as black, and the night sky appears white. Astronomers often find this is an easier way to look at the images than the normal way, where the stars should be white and the sky would be and the night sky would be black. And on the right-hand side is the image that we actually used to find it, which is an image taken in the infrared. And in the infrared, because the star is very dim and cool, it looks actually much brighter compared to the other stars. So that was one reason we picked it out. And then second of all, we looked at the old photographic plates and saw it was moving. I think the reason we can't see it in 1953 was the bad luck that it was right in front of this other star that you can see there, the one that's not moving. And so that's why it didn't appear in any of the classic catalogs that astronomers compiled in the 1950s, 60s, 70s, or 80s, looking for stars, but it was sitting there waiting for us to find it when we had a better sky survey. Now, what is there to do here? Well, 2MASS was the name of the survey. We took pictures of the entire sky using infrared cameras that had just recently been developed at that time. 2306292 tells you exactly where it's located in the east-west direction on the sky, and -050227 tells you where it's located in the north. So this is a good system for astronomers because you could specify every single thing that the survey sees just by describing where it's located on the sky. The bad news, of course, it has names that are so long that even people who write papers about them can't remember the names, right? But bottom line is, the important thing is that this star is only 40 light years away. So big compared to Proxima Centauri, but very close compared to most stars in the sky. All of those background stars that you saw in the other images I showed you are hundreds, if not thousands, of light years away. It's still part of our galaxy, but not doing anything particularly interesting. It's a very small star. It's only about 9% the mass of the sun. Its size is only about 1/10 the size of the sun, and it's very dim. That's why, even though it's only 40 light years away, it looked fainter than many of the other stars. So I've got the number there, but you can see that it's less than 0.1% of the luminosity of the sun, right? So for every 1,000 units of energy that the sun puts off, this thing puts off half a unit of energy. So not doing very well from that point of view. An artist's depiction of what this would look like if we could put them next to each other is, there's the sun and there's TRAPPIST-1. So you can see it's very small. It's much cooler, so it looks red in this picture. And of course it's dimmer, although you can't really judge that from the artist's view. This is interesting because you might say to yourself, well, if the star hardly gives off any light, then there's no chance of having an interesting planet around it. After all, we'd like to find a planet like Earth, which is warm enough to have oceans on the surface and so forth. Pluto is a great object. We all love it, whether you call it a planet or not, but it's hopelessly frozen, right? So you might say, well, aren't all the planets around such a dim star going to be frozen? But of course, it depends on where you put them exactly. If you put it close enough, then it could have liquid water and oceans on it, right? If you put it, in fact, too close, everything will boil off and it'll be like Mercury. So it's all just a matter of where the planets happen to be located. And in principle, there's no reason why you couldn't have Earth-like planets around very cool stars. So, in fact, the reason we're giving this talk was that if we had sort of an ideal telescope, and I tried to calculate how big the telescope would be that we would need, and I came up with an answer that was more than 10 miles across in space. So we're not going to get any images like this anytime soon. But this is an artist's depiction of the image that we would see through a telescope that was very large and perfect, looking at this star TRAPPIST-1. Now, in reality, I showed you what our images look like, right? It just looks like a blob. That's all we can get. But if we could look carefully enough, we would see there's the star, and it's a big circular bright thing. And then it has 7 planets. And I think if you look carefully at this image, you should be able to see all 7 of them depicted. This is actually at a particular moment in time a few years ago, made for the press release after the discovery. So two of these planets happen to be lined up between us and the star TRAPPIST-1 at the moment that this imaginary picture was taken. So they look like dark shadows, right? Little black circles. And off to the right, you can see more of them, which are not between us and the star. And so they're lit up. And in fact, they have phases just like the phases of the moon. You can see that at this particular moment, some of the planets are lit up pretty well by their own sun, the TRAPPIST-1, and some of them are sort of crescent planets right now. So if we, had a really wonderful telescope, we could get images like that. So I think we'll pause here and wait for the moment in which we can tell the story of how we astronomers have actually discovered these planets and know that they exist there, even though we're not capable of taking a picture like this. How are the planets discovered? Well, a team led by Michel Guillon, who's in Belgium, led a group that they called themselves the Transiting Planets and Planetesimals Small Telescope, which, as you may guess from the name, was designed to come up with the cool acronym TRAPPIST, right? It's not even really an acronym. It's it's the word for a backwards acronym, where they had the word and they invented things that would fit, right? So TRAPPIST, of course, is a group of famous monks in Belgium who make some very excellent beer, and so presumably they thought that this was a very clever name. And so here's a picture of the telescope they used to make these discoveries. What it is a small robotic telescope, small by astronomy standards. It's 0.6 meters across, so it's similar to Mount Cuba's telescope. Not the new one that's being built, but the old one. But it's completely robotic. So they could be there in Belgium, and the telescope down in Chile would move around and then just take pictures of stars every night. And this telescope is not big. You'll notice it's not anything like what I said. It's not a 10-mile space telescope, right? So we'll have to explain how a robotic telescope like this is capable of finding planets. And the story also continues because the TRAPPIST-1 discovered 3 planets around this star, and then that was used to justify using the Spitzer Space Telescope to look at it, which saw evidence that there were actually 7 planets, which we will explain in a moment. And then NASA's Kepler telescope looked at it, and they confirmed that the 7th planet really does exist. The Spitzer people weren't quite sure, and were able to measure its properties. So how does this work? Well, the secret is that you actually take very lousy images of the star. This is a picture of the star as taken by Kepler, and you'll notice it's really a blob. It looks out of focus because it is actually out of focus. And but what it can do is count the amount of light that you see from the star very accurately. And the idea is that if we watch continuously the star, we measure how bright it is, we measure how bright it is, we measure how bright it is, and we keep doing that in the hope that a planet passes between us and the star. And if it does, as we saw in our perfect image before, at this moment, when there's 2 planets passing in front, which is, I guess, a very lucky moment, the star would get somewhat dimmer from the 2 planets. And once the 2 planets move in their orbit, and so they're not in the way anymore, the star will return to its original brightness. So this sounds like a completely crazy technique. One thing is that you have to hope that the planet system is perfectly lined up with you. Otherwise, it's not going to work. So for example, in Proxima Centauri, the planet is not lined up with us, and so Proxima Centauri never gets dimmer from the presence of this super Earth planet. Too bad for us, right? But TRAPPIST-1 happens to not only have a lot of planets, happens to not only be close to us, just 40 light years away, but happens to be lined up perfectly. It's sort of a 1 in 100 chance, maybe even 1 in 1,000 chance. And so the reason they needed to have a robotic telescope is that they found their 100 favorite nearby dim stars and had to measure them all. And then they got lucky that one of them actually had planets, right? And they got a bit lucky because there aren't any famous TRAPPIST-2 or TRAPPIST-3 out there. This was actually the only planet they found. But they found the best one, so it was a big success. So here's a video I'm going to play. And what it's going to show you is first will just be an animation showing you that, of course, the planets are going around the star. And then it will shift to showing you the actual data that was taken with the Spitzer telescope. And so what you'll see on the top will be an animation showing what the star and the planets are doing at that moment in time. And you'll see the planets moving back and forth and sometimes passing in front of the star. And on the bottom, you'll see the actual data measured, which will be measurements of how bright the star is. And so you'll see it going along, and then every so often it will dip due to a planet being there. So let's see if this works for us. So here, of course, is the concept, right? Here are our 7 planets going around. The innermost one goes around the fastest, and the outermost one goes around the slowest. This is Kepler's laws that were discovered many centuries ago in our solar system. It's exactly the same situation for these guys. So there's a side view, which happens to be our view. And so you notice there was planet C and planet B just crossed. And in a moment, F and G are going to cross. And so you can see there, we have, of course, color-coded the planets and labeled them to make it easier for us. But notice how often B crosses because it's the closest one. And so we can see it going by a lot. You can see that sometimes the data is missing because the telescope had to beam its data back to Earth and couldn't observe during that time period. So sometimes there's gaps. Planets E, C, and B just went through. Notice that we can't tell the difference when the planet goes behind the star. The planets are so dim that even though you might say, oh, we can't see the planet anymore, that's so little light that we can't actually measure that at this point. And then they go. And sometimes really cool stuff happens, like multiple planets cross at the same time. There goes B again, right? And here comes B. Yep, there it goes, right? And so you can see a little dip downwards on your screen every time, right? You'll notice that there's a lot of static. The dots that represent the measurements of the brightness of the star. I'm going to repeat the video while I talk. Bounce around a lot. That's the inherent limitation of how well we can measure the brightness of this particular star, right? If we had a bigger telescope or the star were brighter, then we would have been able to do better, but that's the best we can do. So you can notice that if the planet were too small, we wouldn't have even seen it. And the nice thing about this is because this is a very intrinsically dim star, these dips that we see, which are not labeled, but represent approximately 1% of the light going away, mean that the planets are about the size of Earth, right? If a planet the size of Earth transits a star that's like the sun, it only blocks out 1/10,000th of the light, and that's very hard to measure. But here, because the star is smaller, the planet can block more of the light, and it makes it easier. Notice, too, that we just saw planet D go by, that planet D's dip is not as big, and planet H's dip is not as big. And that means that the planets are actually smaller. They're not blocking as much light as, say, planet B does. So we can measure the sizes of the star, of the planets, because we know the size of the star, from this kind of measurement. So even though we don't have an actual image of the planets, we do have a lot of information that we can learn just by measuring what is called this light curve, right? Of repeatedly measuring it for a long period of time. The artist's view of what this all amounts to is right here. On the top, we show you what the TRAPPIST-1 system might be like. So there are the planets. Astronomers always name the first planet B because I guess capital A stands for the star itself. And so the first planet is lowercase b, and then there's C, D, E, F, G, and H. Those are the names that are usually used, at least by astronomers. But all of this is like our solar system, but much closer in. And so on the bottom, we show the scale of our familiar solar system, where you see Mercury, Venus, Earth, and Mars, all of our favorite planets, right? Jupiter is too far off to be on my screen. And the whole TRAPPIST-1 system would fit in a tiny little region way inside of Mercury. Right? So somehow this star, even though it's very small, has 7 planets the size of Earth, right? But all packed in really close. So that's a bit of a mystery. How that happens is not fully understood, but it is consistent with the idea that planets exist around many stars. All right, well, this is a little busy picture. It shows you artist's conception of what the planets might be like on the top, based on the size we measured. It also has a bunch of numbers, which tells you the orbital period. In other words, for that planet B that we kept seeing crossing, it goes around the star in just 1.5 days. Right? So we're used to the Earth, where a year is 365 days. On this planet, a year is 1.5 days. Right? That's Earth days, of course. Right? And the outermost planet, well, I can't see H on this, sorry, because of the way my screen is laid out. But planet G, for example, goes around in 12 days, and I think planet H goes around in 30 days, but I don't know if it's on this screen. Yep. You can see that planet D is a little smaller, just like I told you. And then one of the interesting things about these planets being so close to their stars is that they're in a situation very similar to our situation with the moon. You know, probably, that the same side of the moon always faces the Earth. This has been an effect of billions of years of tides affecting the moon so that it ultimately becomes locked so that one side always faces the Earth. The same thing would happen to these planets, meaning that one side of the planet always faces the sun, TRAPPIST-1, and one side always faces away. So if you're on one side of the planet, it's always daytime. If you're on the other side of the planet, it's always night. This is kind of interesting then. So for example, in planet D, what the artist has drawn, and we'll see a bigger picture of this later on, is that on the side D, it's probably very hot, and it's probably, at best, it's like a desert. But on the night side, it might be quite nice, right? Because depending on how the heat is moved around by the atmosphere, there could be winds from the hot, dry side that come around, and maybe the other side's okay. In planet E and F, we can sort of imagine that they might have oceans on the day side, and on the night side, it might be frozen all the time, right? Think of, you know, all the videos we watch on Netflix or BBC or whatever it is, where we see the North Pole during winter when things freeze during the 6 months. Here, it's going to be winter forever. Another scale that you might think about is comparing the size of this planetary system to Jupiter and its moons. And you can see that in that case, planet B is about the same distance that Callisto is from Jupiter, right? So if you could think of it as a very big version of the moon system around Jupiter, or a very small version of the solar system. You know, we're not really sure what's the more productive way to think about it. And then again, a size comparison is that although TRAPPIST-1, the star, is just a little bit bigger than Jupiter and much smaller than the sun, the planets themselves, shown in the box here for TRAPPIST, are all much bigger than the moons of Jupiter, and in fact are all around the size of Venus and Earth. And that's why we sometimes say that they're Earth-like. We're not going to say that they're Earth-like in the sense that you can grow plants there, that you could take a swim. We don't know, right? But they're Earth-like, that at least they're the right size. And again, this is the artist's conception that I told you about before. So we can imagine that the innermost planet must be extremely hot, right? It's hopelessly hot. They've drawn it to look like Jupiter's moon Io. The outermost planet must be totally frozen, but in between, some of these planets might be the right distance. This is shown more mathematically on this graph, where they have plotted for you how much light it receives compared to the Earth. So you can see that the Earth is here. By definition, it gets 1 times the Earth illumination. And planet D, look at that, is very similar in density to the Earth and gets only a little bit more light than the Earth does. So it seems very promising. Planet E is, again, very similar in density to the Earth, therefore probably very similar makeup as the Earth. And it gets 70% of the light, which you know, it should be enough to keep it warm, depending on the planetary situation. And similarly, planet F is sort of getting about the same amount of light as Mars, but because it's bigger than Mars, it may very well be warm enough to have liquid water. This idea of having liquid water is sometimes called the habitable zone by astronomers, although many astronomers and planetary scientists criticize this term because it doesn't at all mean it's habitable. It means it's at the right distance, that it gets about the same amount of light as Earth. And so if conditions were the same as on Earth, you could have liquid water present. And so having liquid water possibly present due to the amount of light is a little bit far from actually being habitable, but you know, it's better than trying to live on Mercury or Pluto. Now, this is another video in which the artists in NASA, I think, are very proud of their imagery. So here we can imagine that if we could send a space probe there, which unfortunately, if our space probe traveled at the speed of light, it would still be 40 years to get there and 40 years to get a message back. So that's 80 years at least. But if we had a space probe that could visit, this could be something of what they would look like. Again, this is just an artist's view. But here you can see, okay, well, planet D looks like it'll probably be pretty warm on one side, but maybe it's okay. And then it has its night side. Here's A, B, C, D, E. Here's planet E, which, you know, could, for example, be completely covered in ocean for all we know. And similarly, here we are, a planet covered in ocean, frozen near the boundary of night. And then we go to the outermost planets, where we don't know very much about what they look like. But eventually should be, the outermost one for sure should be completely frozen. And so it's been drawn as kind of an ice ball. Of course, it could be melted under the surface. It could be ocean underneath an icy surface, just as people believe some of the moons of Jupiter and Saturn are. But in terms of growing trees and things like that, it's definitely not too promising. We'll skip this one and instead say that there's one more reason that these transiting planets are very exciting for future study, which is that in principle, we should not only be able to measure the size and the average density, which has already told us that they are rather Earth-like or Venus-like or Mars-like planets, but in principle, we may be able to learn about their planetary atmospheres. And we may be able to actually measure what is the air like on these planets. How is that possible? It's by using the same method we've been using, the transiting method of seeing how the brightness of the star changes when the planet goes in front of it, but by making much more precise measurements and at many different wavelengths of light. And so here are two diagrams that are supposed to be expressing the same thing, both put out by scientists to explain it. So I decided to put them both here in the hope that one of them is any good. But let's imagine on the left-hand side, two different planets, which are, as you can see, identical planets in terms of their size, the amount of rock and, you know, ice and metals that make up the planet itself. But one has a very thin atmosphere and one has a big, thick, puffy atmosphere. What difference would that make to us in our measurements? Well, the one with the thin atmosphere, light would pass by and it would not be passing through an atmosphere, let's say, if it missed this planet by, let's say, 100 kilometers, right? There's no atmosphere there. It goes straight through. No light is blocked. Life is easy. But the one with the puffy atmosphere, perhaps traveling and you just missed the surface of the planet by 100 kilometers, you do pass through the atmosphere and the air. What happens to the light then? Well, it depends. If it's a wavelength of light where the atmosphere is transparent, not much happens. So it just passes through and it doesn't block any starlight, no problem. But maybe it's a wavelength of light that does get blocked. For example, as you may know, for the Earth, the amount of water and the amount of carbon dioxide in the atmosphere are very important for controlling the temperature of the surface of the Earth. Because these wavelengths of light these molecules block certain wavelengths of infrared light, and so they cause light to be absorbed in the atmosphere. And so you could imagine that if it's the right wavelength, that water would absorb you, and if the atmosphere has water vapor in the atmosphere, then the light will be blocked, and the planet will look bigger. It'll block more starlight. On the other hand, if there's no water in the atmosphere, then the planet will look smaller because the light would go through. And if you make the measurements at other wavelengths, you're sensitive to the presence of different molecules. So the size of your planet should be varied depending on what type of light you're measuring. Now, there are a lot of complications with that, and the plot on the bottom is a little warning that if your planet happens to be completely covered in clouds, like, for example, Venus is, then clouds are good at blocking all types of light. So the planet will just look a little bigger than it normally does, and you won't learn anything about what the composition of the atmosphere is. You'll only learn that it has clouds in it. And you won't know what the clouds are made of, and you're out of luck. So astronomers are very worried that planets could turn out to be cloudy, and that will be a real pain for us, but we'll have to just see what happens. This technique has been used on the TRAPPIST planets using the Hubble Space Telescope. The data are shown here for 4 of the planets. The data, the actual measurements, are the green dots, and each one has a fairly large error, so a line has been drawn vertically that show you the range that it plausibly might be. And to help you, a flat dotted line is there, drawn through there, and you would sort of see for yourself that these measurements don't really look much different than the straight dotted line. That's actually good news. For an Earth-like planet, we wouldn't expect Hubble to be able to have been able to measure anything, and we would expect a flat line to appear. If, on the other hand, these planets were not at all like we thought they were, if they were not Earth-like, but rather were covered in a giant atmosphere of hydrogen, like the planet Neptune is, for example, then we would have seen something very different from the flat light. We would have seen something like this weird purple shape that's shown on the data there. And you'll notice that the green dots, or the green crosses, don't really look like they're making the purple shape here, right? They don't go up and down, they're just flat. And so that is evidence from these measurements, which admittedly are somewhat abstract, that these are not planets that are like Neptune. They're not miniature versions of Neptune and Uranus. They're not miniature versions of Jupiter. They really are planets like the Earth. We can't say much about their atmosphere yet because Hubble is just not a big enough telescope. It doesn't have the right types of cameras on it to make the measurement. But this is a proof in principle that at least has ruled out some possibilities. Now, I'm going to show you a real plot from a scientific paper, only because since the measurement hasn't been made yet, I haven't found a nice press release version. So this is a calculation of what you might measure for different possibilities of TRAPPIST-1 planet atmospheres using the future telescope named James Webb Space Telescope, which supposedly will be launched later this year. And if it is, it will be the best thing that's happened in astronomy since Hubble Space Telescope. And in particular, you can see there's a bunch of colored curves here. And I want you to look where the number 10 is. That's 10 micron light in the infrared. And you'll see that depending on the color of the curve, it looks very different, right? One possibility is it goes way up high, right? And the other one at the bottom goes down there low and in between. Why is this important? This is calculating what the size of the planet would be at that wavelength of light if it has ozone in it. If it has a lot of ozone, right, you might get the curve that goes up at the top. If it has the same amount of ozone as the Earth, that's the orange one, kind of in the middle, right, but a great big spike still. And if it has no ozone at all, it should be down at the bottom. So you could imagine that if you can measure how big the planet looks at 10 microns and how big the planet looks at 11 microns, where you notice all the curves are exactly the same, you will be able to tell whether or not it has ozone on it. And that, of course, has been of great interest to astronomers because we believe that the reason that Earth has oxygen, and in particular ozone, O3, is because of the presence of life, right? There are a tremendous number of plants, right? Bacteria, whatever they are, that are putting out huge amounts of oxygen into our atmosphere. And that is the only reason that if you look at the Earth today, that there is ozone. If you look at Venus, you would not see ozone. If you look at Mars, you do not see ozone because those are dead worlds as far as we can tell. Same with Neptune, same with Jupiter. You wouldn't see any ozone on those planets. But the Earth has ozone because of the presence of life. Similarly, you can see other parts of these curves are labeled that you could find out that whether or not there's water in the atmosphere and whether or not there's carbon dioxide. So, if you did this experiment with Venus, you would see that Venus has no water, but has lots of carbon dioxide and it has no ozone. And you'd probably say, well, that doesn't seem like a very good place to live, right? If you do the experiment with Earth, you would find huge amounts of water, huge amounts of ozone, and you'd say, oh, that's a great thing for life. Now, let us worry that if we ever do make this experiment, if we ever do measure ozone, that will be the day that people will then check out their calculators and they say to themselves, are there any ways chemically to make ozone other than life? And of course, unfortunately, they've already looked into this, and the answer is, well, yes, maybe. It could be that you can make ozone in some other way than life. Nevertheless, I think this is a very encouraging idea that in principle, you can imagine that with future telescopes, either James Webb Space Telescope or this next generation of telescopes, which are built in the 2030s, that we may be able to actually measure not whether planets that are Earth-sized actually have atmospheres with water or with ozone in them or carbon dioxide or all the molecules, well, not all, many of the molecules that are familiar to us that are very important in our biosphere. And on the contrast, we may be able to see that many planets, in fact, are not very promising. They may look like Venus, right? So that's the possibility. I will warn you that this is a very difficult measurement. You can tell that from the scale there. You'll notice that the scale says that in order to tell the difference between these different models, we have to be able to tell the difference between 0.0850 and 0.0855, right? Which is a difference of less than 1%. And yet I showed you in the earlier thing that we could hardly measure the brightness of the star to 1%, to better than 1%, right? And so now we have to measure exactly how deep the dip is with no errors. And so it turns out in order to do that, we not only need a big telescope like James Webb Space Telescope, but you have to watch it transit many, many times. And so to measure an Earth-like planet, it's very likely that you would have to measure something like 50 transits. The good news is that for TRAPPIST-1, the planets we were talking about transit once every 10 days. So if you point your telescope at it once every 10 days, you observe 50 transits, it only takes you, right, less than 2 years to do it. So that's good news. For an actual Earth-like planet around the sun that was transiting, of course, its period would be 1 year. And so to measure 50 transits would take 50 years. That's a very bad project for someone's career, right? It's, exciting for long term, I suppose, for science, but very difficult to have a telescope even operate for 50 years straight, much less to have someone do the project. So your takeaway messages, and then hopefully people will have some questions, is that TRAPPIST-1 is an example of a nearby star. It's very similar to other nearby stars, but it's about the dimmest and smallest star that you can have. But it has a remarkable number of planets, 7 Earth-sized planets, and it just happens to be that these are lined up perfectly for them to transit. And as a result of this, we were not able, we astronomers, we're not only able to measure that the planets exist, but we know how big they are, we know how far away they are from their star, we know how much light they receive, we have a pretty good measurement of what their mass is. That means we know what their density is. That means we know pretty much what the planets are made of. We know that they can't be made of gas. They can't be made, right, just of water ice. They have to be made mostly of rock and iron. And some of them are at the right size and distance to be Earth-like planets. Now, I will tell you, I didn't want to be negative in this talk, that there are many, many things that you could imagine that could go wrong living on an otherwise Earth-like planet that you plop right next to a star, right? This thing is 100 times closer to its star than we are to the sun. And that means you're exposed to an awful lot of particle radiation and other things that we don't usually have to worry about on the Earth. And that might be a big problem. So it would not surprise me at all that in 5 or 10 years, when we have the results from James Webb Space Telescope, we might find out that all 7 of the planets have been really blasted, and they turn out that even though they're at the right, they could have had the right temperature to have water on them. Maybe in reality, they're being zapped, and that's all the life, any life on it has been killed, and the atmosphere and the oceans have been boiled away by some disaster, right? But in principle, at least, we can still imagine that they're Earth-like planets. But the really exciting thing is that we will continue to be able to make measurements of the planets instead of just guessing. So this is a really powerful tool that with sort of present-day technology and near future technology, we, could in principle measure whether or not these planets have oxygen in their atmospheres, whether or not they have water on their surface, things like that, that otherwise are highly difficult to imagine being able to measure because our telescopes just aren't big enough. So with that, I'm going to leave you with that the story. It's been an incredible story of progress. The star wasn't even known 21 years ago. The planets weren't known until about 5 years ago, and now we know so much about them, and so it's very exciting.